On yesterday's lecture, we started talking about trigonometric integrals that involved identities. We talked about writing functions in terms of sine and cosine, and we talked about trig identities that allowed me to write even powers of certain functions in terms of other functions. Now, I gave two problems yesterday, which were this problem that is written on the board here, and this other problem. I'm going to solve both of them right now. Do I have anybody that tried the problem that is currently on the board? You can raise your hand, and if you have an idea of how we should start it, you can show me, like just try to contribute something to how we start the problem. Ideally through your mic, because that way it's a little bit easier for me to discuss it. Any ideas? Okay, hopefully you'll get less shy as we go with the online class. It's a bit difficult to talk to a computer. So we're going to have, we have tangent to the power of 3 times secant to the power of 4 applied to x. We're going to have to do a substitution. That's the first thing. I'm going to do a substitution, and I need to choose which substitution to use. If I want to do a substitution, according to you, what do you think should be the substitution that I choose in this case? What is a possibility for you? Parsa has his hand up, maybe because he forgot, but now he's on the spot.
Well, you could do it with tangent and secant, but the easier way I found was with secant x.
With secant of x, okay. Yeah. So you used secant of x as your u.
Yeah.
Okay, so that's one possibility, and then the other option is to use u is equal to tangent of x. Maybe one of them is better, maybe none of them is better. Doesn't really matter. Okay, so we're going to start with u is equal to secant of x, then we'll see if the one with u is equal to tangent of x works. So the derivative of u is equal to secant of x is going to be du, and the derivative of secant is equal to what? So you remember that this is equal to secant of x times tangent of x, right? And this is multiplied by dx, which would mean that I need to rewrite my integral in such a way that I have a secant of x and tangent of x that come out to see if I can actually write everything else in terms of my variable now, which is u, right? So if I rewrite this integral, I'm going to have the integral of, I have tangent to the power of 3 over here, but I'm going to use one of them for the dx. So that means I'm just going to be left with tangent squared of x. And then I'll have secant to the power of 3 of x, because I'm also going to take one of them for the dx. And I'll end up with secant of x times tangent of x times dx, right? Which means that now I can use that last bit as my du. And then I would have to find a way to write everything in the first integral in terms of either tangent or secant. Now, if I try to write right now I need to write everything in terms of secant, and that means in particular that this term that I have here, which is written as tangent squared of x, should be written in terms of secant. Now, lucky for me, I have that if I have an even power of tangent, there is actually an identity that gives me an expression in terms of secant. So I'm going to go back to the identities that we had from yesterday, and we had that tangent squared of x was equal to secant squared of x minus 1, if I put the 1 on the other side, right? So that means over here, I'll be able to rewrite this as secant squared of x minus 1 times secant to the power of 3 of x times secant of x times tangent of x dx. And now I have everything written in terms of secant, and then I have the term that is going to help me replace du. Do I have any questions about this, or is that okay for everyone? Hopefully that's okay. Right. So I'm going to finish this problem in just a second, but for now, I'm going to see what happens if instead I choose u is equal to tangent of x, right? So that would mean that I have u is equal to tangent of x. This is the second option that I have over here. And maybe I try that first. I need to see if it's going to work because it's not obvious that necessarily all of you used secant right away. So if I choose u to be equal to tangent of x, then I'm going to have that du would be equal to secant squared of x dx. Right, so du is equal to secant squared of x dx. And then I would have to rewrite my integral by separating now the secant to the power of 4 as secant to the power of 2. So that means I would get over here that my integral is equal to the tangent. I can leave like that because that I don't need any of those in order to replace my du. So tangent cubed of x. And then the secant to the power of 4 is going to be written as secant squared of x times, and I'm splitting secant squared of x dx to be my du in this case, right? So that means over here, the du is going to be given by secant squared of x dx. At this point, I can say, okay, well, the tangent cubed of x is fine. That's already written in terms of tangent. But the secant squared over here, again, is not written in terms of my variable u, so I need to rewrite it in terms of tangent. So this is one of those cases in which both of the substitutions are going to work, because even by taking the 2 powers of secant to go along with the du, you're still left with an even power, and you can replace secant squared of x in terms of tangent. So if you look at, again, the identity that we had yesterday, if you have secant squared of x, that's going to correspond to 1 plus tangent squared of x. So you can replace that term like this. So we'll have 1 plus tangent squared of x, and then again, secant squared of x dx. All right. Okay, so these are the 2 possibilities that you might have found if you tried to do this problem and you did at least this part properly. Both of them are correct. They're equivalent. It's just that they're going to give different answers. So that I think I talked about this either last class or when I first introduced trigonometric functions, which is that there's a lot of equivalences between the results, even though they look like different results. So just make sure that you don't freak out as soon as you see an answer that is different to the one that I give. So if I have used u to be secant of x, then that means that my first integral over here becomes u squared minus 1 times u to the power of 3, and then secant x tangent x dx is replaced by du. I know that this means that I need to first distribute and then integrate. So that means I would get u to the power of 5 minus u to the power of 3 du. And when I integrate, that would give me u to the 6 over 6 plus c plus, yeah, the plus c I'm going to put afterward. So minus u to the power of 4 over 4 plus c. And if I back substitute, I'm going to have that this is secant to the power of 6 of x divided by 6 minus secant to the power of 4 of x over 4 plus c. Okay, so this is right answer number 1. So this is the first result, and this is what you should have gotten if you chose u is equal to secant of x. In the other case, you have that by replacing, okay, so do I have any questions about that first example? Or is that all right for everybody? Okay. So then for the second one, I have that if I replace u by tangent of x, I'm going to end up with u to the power of 3 times 1 plus tangent squared, which is u squared, and secant squared of x dx becomes du, which means that I can rewrite this as the integral of u to the power of 3 plus u to the power of 5 du. This is going to give me u to the 5, oops, u to the 4, sorry, over 4 plus u to the 6 over 6 plus c, which if I substitute back into the value that I chose for u over here, which is tangent, means that I have tangent to the 4 of x divided by 4 plus tangent to the 6 of x divided by 6 plus c. Okay, so these are the two possible answers that you might have gotten if you did this problem properly. So this is option number 2 and option number 1. Can I see a show of hands for those of you who got at least one of the answers right? Okay, so not bad. All right, that's good. So that means everybody kind of at least started the problem the right way. I assume that some of you might have chosen secant of x, some of you might have chosen tangent of x. Now, this is a very special case, okay? So this is a special case in which it just happened that both of them worked. So both worked. But in general, what you're looking for is to create an even power, right? So if you create an even power, then you know that you're going to be able to replace in terms of the other function. Because, for example, if you look at here, the whole reason that you were able to replace is because tangent was squared, which is an even power. And the whole reason that you were able to replace here is that secant was squared, which is why you were able to replace it in terms of tangent. If you have different powers, sometimes there's going to be one of the substitution that is going to work and not the other. In those cases, you always should be looking for the one that is going to generate an even power once you separate the terms that you need for the du. So the first thing is to look for the du that you're going to require. And then once you've taken care of that, you're going to see if you have an even power left. If you do have an even power left, you'll be able to replace into the other functions. Okay, so that's kind of the trick for this type of problem. Do I have any questions at all? All right. Okay. So maybe I'm going to leave it for now. So in the other type of question that we had, that might not have been, it should not have been as difficult. So it's this problem over here. So x times cosecant squared of x. Can anybody tell me what technique you should use in order to write this, in order to solve this integral? You have the chat or you have the voice? Nobody tried anything? Can I see a show of hands for those of you who tried the problem? Oh, well, that explains it. If I only have one person that tried the problem. Okay, maybe two people that tried the problem. Okay, that explains it. So on a first look, what is the technique that you would try to use in order to solve this integral?
I actually tried it, but I didn't write the right question. So
oh, maybe I copied it wrong. What did I write?
No, it might have just been me. I don't know. I wrote down x secant squared 8x dx.
Oh, okay, that's fine. It's the same same idea.
Okay. Well,
Okay,
for that
so
one, I did v equals x and dv equals dx, and then du would equal to secant squared 8x, and then u would be 10 of 8x over 8.
okay,
So I
yes.
use integration by
All
parts.
right. So then that means x secant squared of 8x dx. Like that, is that good for everyone? Raise your hand if it's good for you. If I'm asking for a yes answer, in general, it's going to be a raise your hand. Okay, good. So now who tried this problem? Because maybe that makes a bit more sense. All right, okay, that makes sense. Yeah, okay, so it's the same idea, I just wrote the different problem because I wanted to complicate it a bit more. Good. And then who tried integration by parts for this problem? Great. All right, the numbers are rolling a little bit better with this one. That makes a bit more sense. Okay, so we have v is equal to something, du is equal to something, oops, is equal to something else, oops, is equal to something else. And what you said, it was Matthew that was talking, right?
Yeah, I
Yeah,
said
okay.
v was x, dv was dx, or was it dv I said was dx, or I don't know.
Yeah, that makes sense.
Du was secant squared 8x, and then u was tan of 8x over 8.
Okay, that's good. Okay, can I see who did the same thing? So v is equal to x, dv is equal to dx, du is equal to secant squared of 8x, which means that u is equal to tangent of 8x divided by 8. Okay, so the choice of b should be pretty natural because we know that the derivative of x is going to be easy to evaluate. And also because we know that the integral of secant squared should not be too difficult to evaluate, right? So those are two things that we need to consider in general. So the derivative has to be something that is easy to differentiate. And the integral also should be easy to evaluate. Maybe the thing that's a little bit tricky in this case is that we need to make sure that we divide by 8 because the inside function is not just x, right? The inside function is 8 times x, which means that we need to divide by 8. At this point, we're going to have u times v, which is x times tangent of x, tangent of 8x, sorry, divided by 8 minus the integral of dv times u, which is tangent of 8x divided by 8. And here you have to be really careful because if you have it divided by 8 here, that means you need to include it when you rewrite the second integral. And then the dv in this case is just dx, right? So this is the integral that we have. At this point, okay, so the first term is not going to change, and the only thing that is going to change is going to be the second term, which now I have to integrate separately. So I'll have that this is going to be x times tangent of 8x divided by 8. And the second term will be 1 over 8. I'm going to put the 1 over 8 in front, and then I can take the antiderivative of just tangent of 8x. So the derivative of tangent is just minus ln of cosine of 8x. And then I can divide this by 8 because the inside function is not just x, it's 8 times x. And then I have plus c. Okay. Show of hands, who got this? Okay, not bad. So at this point, we have that the final answer for the first term is x tangent of x, tangent of 8x divided by 8, and then minus, now this is minus times minus, so I'm going to make that a plus, and then I have 8 times 8 at the denominator, so that's going to be 1 over 64, which is 8 times 8, and then times ln of absolute value of cosine of 8x plus c. All right. So this is the final answer for this one. This is just a bit of a tricky integration by parts. The only tricky part is really to divide by 8 every time that you're integrating a function that has an inside function, which is a constant times x, right? So that's kind of the trick in these cases. Aside from that, it's just a very standard integration by parts. I also want to mention, I went over a couple of the questions in Peerwise yesterday. There are some of them that are really good. There's two things that I want to notice. The first thing is that you should always write a statement, an instruction for what people should do. So if you write an integral, it's not enough to just write the integral. You have to say evaluate the following integral or solve the following integral or something like that. And if you find a mistake when you're solving the questions, you should put that as a comment. Okay, you should put that as a comment that will send a message to the person that wrote the question so that they can correct it if need be. All right, I see that a couple of people have their hands up. There's a question. Lauren and Matthew?
Yeah, when I upload my question, it wouldn't let me upload like the explanation because I guess the file was too big or something. Like,
oh, that's possible, yeah.
Yeah, so do you want me to just send it to you over MIO if I can?
You can send it over MIO, but the explanation is also very useful for the students. So what you can do instead is at least type some of it, right? So for example, if there's a part that is integration by parts or a substitution, you can at least give the basic instructions of what should be done.
Okay, thank you.
Okay, because that's useful for other students as well. Are there any other questions? Okay, Lorena took her hand down, so that means either it was the same question or it was just a mistake that the hand was out. Okay, so I think this covers the first couple of examples that I wanted to cover today. I'm going to keep going with a couple other integral examples. You're going to see the next three examples actually require that you simplify functions in terms of their original expressions using sine and cosine very frequently, or that you simplify a couple of things first. So the following integral is going to be the integral of cosine of x plus sine of x minus 1. The whole thing divided by cosine of x squared. Cosine squared of x with respect to x. Okay, so it's cosine of x plus sine of x minus 1 divided by cosine squared of x. You can write that down and you'll have 2 minutes to think about it. My hint here is to try to simplify as much as you can. Okay, does anybody have an idea of how to start this problem? Maybe what is the first thing that we should do? We can separate the fraction, yes. So what we can do is just divide each of the terms separately. Okay, so hopefully that was the first step for everyone. This is the same as when we have a huge polynomial at the top and then just one exponent of x at the denominator. Same idea over here. So we're going to have cosine of x over cosine squared of x plus sine of x over cosine squared of x minus 1 over cosine squared of x, right? Now, I don't know if anybody had this reflex of maybe writing cosine squared of x as 1 minus sine squared of x. If you did, make sure that you don't do that again, because introducing a minus into the denominator of a fraction is not really going to be helpful, right? In general, if we have just one term at the denominator, that's a lot easier to handle than if we have something that has a sum at the denominator. Partial fractions should have been a hint on that. It's not necessarily the best idea. Now, the advantage of having everything as just a single term over here is that of the identities that we looked at yesterday, all of them were telling me how to write each one of the functions, of the trig functions that I have, as just one fraction. So presumably, if I have just pieces with one fraction and no sums, I will be able to write them again in terms of either tangent, secant, cosecant, cotangent. Okay, so I'm going to start by simplifying the first term over here, which is the integral of cosine of x over cosine squared of x. So I can cancel one of these and the numerator. So that means I'm going to end up with 1 over cosine of x. In the second term, I have sine of x divided by cosine squared of x. I'm going to leave that for now. And in the last term over here, I'm just going to rewrite this in a way that maybe becomes easier to see afterward. 1 over cosine squared of x is the same as if I wrote 1 over cosine of x the whole thing squared, right? These two things are equivalent. And then this is with respect to x. So that means I can now try to rewrite this integral in a more efficient way. So 1 over cosine of x, what function is that? On the chat or with your voices. 1 over cosine of x is?
Secant of x.
It's secant of x, yes. Secant of x. And then I have sine of x over cosine squared of x. I'm also going to try to rewrite that. But the thing is that I have just 1 power of sine of x at the numerator and 2 powers of cosine of x at the denominator. So that means that if I'm going to rewrite that term, maybe a good way is to try to split the denominator into 2, right? So I'll have sine of x over cosine of x, and then I'll have whatever is left at the denominator. So here, for example, I'll have sine of x over cosine of x. That way I have just 1 power of each one of them, and then times 1 over cosine of x. So that way I have the 2 powers of the cosine over here and just 1 power of sine at the numerator. And then if I have 1 over cosine of x, the whole thing squared, this is the same as 1 over cosine of x, where I have applied the square over here because 1 is just 1 squared. All right, at this point I have secant of x. Now, sine over cosine is equal to what?
Tangent.
Yes, tangent of x. And then 1 over cosine is, again, secant of x. And in the last term, I have 1 over cosine is secant of x. And then you have that whole thing is squared. So that means this is going to be secant squared of x with respect to x. By rewriting everything in terms of secant or tangent, now we know the integral of secant of x. This is one of the integrals that we need to know. Tangent of x times secant of x is the same as secant times tangent, which is actually just the derivative of secant. And secant squared is just the derivative of tangent. So that means I can now integrate each one of these pieces separately and be done with the problem. So I'll have integral of secant of x is going to be ln of absolute value of secant of x plus tangent of x. This is one of the integrals that you need to know, plus the integral of tangent times secant, which is just secant of x, and then minus the integral of secant squared, which is just tangent. So this is minus tangent of x plus c, and this is the final answer. Had anybody gotten this answer? No one? All right, so no raised hands. All right. Had anybody gotten somewhere along the way in this problem? Okay. All right. Okay. So it's just a matter of probably not finishing the problem. Most likely, the difficult part here is to identify each one of these in terms of sine and cosine. So I think, for example, for this problem, the part that might be a little bit trickier is to split this one into sine of x over cosine of x and 1 over cosine of x. I think the trick for that is to try to actually just make the powers at the numerator and denominator correspond. Okay, so if you do that, then eventually you'll end up with one of the functions that is defined in terms of sine and cosine. Okay, so I'm going to give another problem. Technique is going to be very similar. You can try it on your own. So that's going to be the integral of cosecant times cotangent divided by, oops, no, not yet, minus sine of x divided by sine of x times cotangent of x with respect to x. And for reference, this is a problem from a previous final exam. So this is something that you should be able to do. So I'll give you 2 minutes to get started on the problem, and then I'll correct it. All right, so at this point, hopefully everybody started the problem the same way as the previous one, which is to say having a minus of the numerator is not really helpful. So we're going to try to divide this into 2 different fractions and then see what we can do with each one of them. So we'll have the integral of cosecant of x times cotangent of x divided by sine of x times cotangent of x minus the integral of sine of x over sine of x times cotangent of x dx. Right? So for the first fraction, you have that the cotangents of x are going to cancel, and for the second function, you have that sine of x at the numerator and denominator are going to divide out. At this point, we have to figure out what to do with the cosecant and the sine at the denominator. So if you see it right away, that's fine. You don't have to show more work, but if not, then I'm going to show how to get to the following result. So cosecant over here is actually just 1 over sine of x, right? So that's what we have at the numerator here. And then at the denominator, we have sine of x again. In the second term, we have 1 over cotangent, right? Because I divided the sine of x out, but I still have 1. And if I have 1 over cotangent, so yesterday, one of the identities that we knew was that cotangent of x is equal to 1 over tangent of x, which means that cotangent is the inverse of tangent. So that means that tangent is also the inverse of cotangent. So if I have 1 over cotangent of x, this is going to be the same as tangent of x with respect to x. All right, and then if I rewrite 1 over sine, again over sine of x, this is going to be the integral of 1 over sine squared of x, so I have 2 factors of that, minus tangent of x with respect to x. Now this term I know how to integrate, but I still have to write this in a way that I will be able to integrate it. Can anybody tell me what 1 over sine squared of x is going to be? One over sine squared of x?
Ooh.
Oh. What's 1 over sine squared of x? Was that an answer or just?
Is it cosecant squared x?
Cosecant squared of x, yes. There you go. So now we can actually integrate this because this happens to be one of the functions for which we know the antiderivative. Same thing for tangent. So the antiderivative of cosecant squared is minus cotangent of x. And then I have minus the antiderivative of tangent of x, which is minus ln of absolute value of cosine of x plus c. And then I can just simplify because I have a minus times minus. So that means I have minus cotangent of x plus ln of absolute value of cosine of x plus c. All right, so this is what you should have gotten. Can I see a show of hands for those of you who got the right answer? Okay, that's not bad. Can I see a show of hands for those of you who either got the right answer or got some of the work along the way? Okay. All right, that's good. So there's going to be a couple of problems in the problem set that requires you to actually evaluate these integrals by simplifying. Okay, so if you see something that looks very complicated, you don't know how to do a substitution or something like that, it might be because you have to simplify things before you do anything else. Do I have any questions? So Megan, you still have your hand up. Is that because you forgot to take it down or because you have a question? All right, no answer there. All right, so I'm going to move on to the next problem. If there's a question, you can unmute yourself, and even if you interrupt me, it's not too bad. Next problem then is going to be the integral. So evaluate the following integral where the integral is. The integral is integral of secant of 2 times secant of x minus cosine of x plus 2 divided by cotangent of x dx. Okay, so 2 minutes for this one. Okay, so at this point, you should have probably gotten to a similar conclusion than before, which is that you need to try to separate this fraction into 3 pieces. If you did that, you should have gotten integral of 2 secant of x over cotangent of x minus cosine of x over cotangent of x plus 2 over cotangent of x dx, which means that I need to simplify still a couple of things. Now, we know that dividing by cotangent of x is the same as multiplying by tangent of x, which is going to come in really handy for these two over here. So that means the first one is going to become 2 times secant of x times tangent of x. That already looks like a derivative that we know. For the second term, though, I have cosine of x, and I am going to multiply by tangent of x. But the thing is that cosine of x times tangent of x is not something for which we know the antiderivative. So instead, what we're going to do is rewrite this like tangent of x in terms of sine and cosine right away. So it turns out tangent of x is just sine of x over cosine of x. So just for reference, this is tangent of x. So I'm multiplying by tangent of x, and I'm rewriting it in terms of sine and cosine right away. And then for the last term, you have plus 2 times tangent of x dx. And here you see that the advantage of writing this as an expression in terms of sine and cosine is that I can now cancel cosine of x at the top and at the bottom. And now I can evaluate the integral of each one of these terms separately. So I'll have 2 times the antiderivative of secant times tangent. That's just secant, remember classics. The antiderivative of minus sine is plus cosine. So I'm going to have plus cosine of x. And then the antiderivative of tangent of x is going to be minus ln of cosine. So that means this is going to become minus 2 times ln of absolute value of cosine of x plus c. Okay, so this is the last example I think that I plan to cover today. Now, what I expect you to do before, what? Yes, cotangent is 1 over tangent. Okay, Erin, can you turn on your mic? I'm not sure what you're referring to.
Because you said that it's for you said sine over cosine, but isn't it cos over sine?
Yes, so it would be cosine of x divided by cosine over sine, right? So that means that if you are multiplying it, that becomes cosine of x times sine over x over cosine of x, right? So the whole thing is that you're dividing by cotangent, not multiplying by cotangent.
Okay, yeah.
Does that make sense?
Yeah.
Okay, so then once you can either do this by replacing cotangent of x in terms of sine and cosine, while it's at the denominator. But what I did is I said, okay, well, cotangent is 1 over tangent. So that means that if I'm dividing by cotangent, it's the same as multiplying by tangent. And then I replace tangent in terms of sine and cosine. All right, so at this point, this is the last example that I plan to cover today. You have a worksheet about trigonometric integrals that you can finish working on right now. I'm going to stay at this meeting until the end of class, which is still about half an hour. If you want to practice problems with trigonometric integrals right now, I think that would be a good idea. That way you don't have to work on it too much outside of class, and then I'll be here to answer questions. If you are not interested in getting help, you can leave now. This is the end of the lecture. So just, yeah, you can basically use the rest of the class today as a practice session / office hours.